Okay, so I want to give you an introduction to Epsilon-Delta proofs, and it's a topic that if you decide to go further in your calculus studies, you'll look at this again, and you'll look at a lot more complicated functions, and really rigorously study this. But for our class, we're going to look at this concept, and we're going to keep it to more basic functions, just to kind of, just we're emphasizing conceptually this idea of what it really means to rigorously prove a limit exists. Okay, so I think there's a typo on my notes. This whole part, this except possibly at C, ignore that. So just say let f be a function defined in the open interval containing C, and let L be a real number. So if you are saying the limit as you approach that C value is equal to L, then you can say the following. Okay, and so that's again, kind of going back to this picture. So if you think, as you approach your C value, right, that's right here, as you get closer and closer and closer to that C value, the question is how close is close enough to guarantee, like how close you have to be to guarantee that your Y values are actually getting closer and closer to the value that you think or you're claiming to be the limit. Okay, so this distance that's away from the x-axis, I should say on the x-axis, we want to make that really small, and so that's a delta. So we want this delta, that distance, to be really, really small, that's away from our x value. So then the question is, well, how close would you be then on the y-axis? And so there's a relationship between this delta and this epsilon. So what it's saying is that for every distance, every positive distance away from what you think is the limit. So you're seeing the pattern, let's say, on the table of values on your graphing calculator, and you're within a certain interval, and you think, you know what, I think I'm close enough to make a claim to say that that's the behavior, the y value is this. So for every distance away that you are from what you think is that limit value, you must show that you are a certain distance away on the x-axis, and it converges to that point. So for every positive epsilon, there's a positive delta, such that you can get close enough on the x-axis to guarantee that this right here, that I'm circling, that you'll be close enough to claim your limit value works. In other words, what the function's behaving and what the limit value is, that difference is less than that interval that you have claimed to be, that you can say, oh, here's a limit. Okay. And, again, it's a pretty sophisticated and abstract idea, to start with. So it's going to take some time to kind of process this. So what I'm going to do is I'm going to go through this first example again, very, very slowly, and try to emphasize the concept behind what's happening. We're going to start with a simple function, a linear function that has no discontinuities. It's very predictable. So in terms of evaluating the limit, I could just use a direct substitution, right? Like if I wanted to know what's the limit as x approaches 2 of f of x, I could simply just evaluate f of 2, which is 4. So I'm going to claim that the limit value is 4. And so, again, if you're thinking about a graph, 3x minus 2, as x approaches 2. So here's our point. So the question is how close can I look at the range of values? How close do I have to be then on the x-axis to guarantee that the range of values will become 4, right? So that's kind of what we're going to start with. We want to start with by saying, well, how close do we need to get, right? What if I want to make the conclusion that the then part is true? I'm going to start there to say, okay, as long as I can get here, then I know this part is true. So I'm going to start with the end in mind. I'm going to start with, I'm going to start with this idea that, okay, I want f of x minus my limit value. I want to be within 1/100th. So I want my pattern, my range of values, I want to be within 1/100th. And then the question is, well, how close would I have to be on the x-axis to guarantee that that limit would be true? Okay, so that's kind of our goal. We will always be given you always will be given your epsilon. So this right here is a specific epsilon. That's a distance on the y-axis. Okay, so it's going to always say it will either say I want a specific epsilon or for any generic epsilon, which is kind of our second part. So the distance on the y-axis I want to be away is 1/100th. Okay, so let's replace. Let's go ahead and replace the function with what the function is, which we said was 3x. What was it? 3x minus 2. Yes, 3x minus 2 minus 4 is less than 1/100th. Or that's 3x minus 6 is less than 1/100th. Now, I'm going to divide this 3 across to the other side. I'm going to factor out that 3. So I get x minus 2 is less than, and I can even make this like 1/100th like that. I think it's going to make it easier. Divide the 3 across. So x minus 2 is less than 1/300th. And the reason I'm leaving this x minus 2 is because that's the characteristic format right here. Like, how far do we need to be away from 2? What distance do I have to be? And so I can see, right here, my distance I have to be away is 1/300th of away. So on either side of 2. So again, if you think about if you were on a number line, so 1, 2. So here's 2. So as long as you are within 1/300th in either side, as you get close enough to that x value, that is going to tell you that your y values will then converge to 4. So if you can be close enough, if you want to be 1/100th away on the y-axis, then you just need to be 1/300th away on the x-axis for that to work. So in this case, I'm going to choose my delta. So choose delta to equal 1/300th. That distance, as long as you're within 1/300th on the x-axis, your epsilon would hold true. And then you could even generalize that. So I'll go through the process again. So you could generalize that. Maybe I'll pick this color. So if you want your function to be less than 4 for any given epsilon. So let's just use epsilon, right? The process is the same. So you'd say this is 3x minus 2 minus 4 is less than epsilon, or the absolute value of 3x minus 6 is less than epsilon. Factor out the 3, divide it over, so you get x minus 2 is less than epsilon thirds, and there's your delta, right? So choose delta equal to epsilon over 3. So if you choose for any, because think about what it's saying, for any positive epsilon, there exists a positive delta. So whatever epsilon you pick, if you divide it by 3, that's your delta. It gives you that relationship between the two. Okay, I'm going to stop this video, and I want you to go back and just look at what the definition is, and look back at your steps. And then I'm going to do a second video of the next example. And my hope is that you see this a couple times, and then we'll see it in class again tomorrow, and then we'll start to have a good understanding of these Epsilon-Delta proofs, and hopefully give us a more rigorous way to verify these limits do in fact exist.